Hey guys, it's Mr. Wolf here. I'm going to be basically walking you guys through the Target 3 sheet, going over the main ideas that we explored in class today. And so for your sheet, you guys should have the target typed up here and the target typed and have this typed right here. So from here on out, basically just follow along and write basically as I'm writing, and I'll explain what I mean as I go through each part of this. All right. In addition to that, what I want you guys to do is kind of split up your paper and make like just a little bit of a dotted line here, just to make sure that you're kind of having similar spacing as me. All right. So conservation of momentum, if we had to sum this up, we're basically going to say that the total momentum before is going to equal the total momentum after. And we're going to box that up. This is really summarizing the main idea of Target 3. All right, so let's break this down. What do we mean by this? So here's a situation before and after. And we have a blue ball moving to the right at 5 kilogram meters per second, and a white ball moving to the left at -3 kilogram meters per second. Since they're going at each other, they're eventually going to collide. So that's going to be the after. It's going to send the blue ball going to the left now at -4 kilogram meters per second. And the white ball is going to be traveling at 6 kilogram meters per second. All right, so here's our situation. We're going to be looking at this at multiple different ways. The first is let's just look at the change in momentum of my one object. And we've done this with target 1. So the change in momentum, my blue object. All right. I'm going to be looking at my final momentum minus my initial. And that's going to give me a momentum of -9 kilogram meters per second. You don't have to write this if you don't want to. I would take it out if you haven't written it yet. All right. And then my change in momentum of the white ball, I'm going to use the same idea that I did here, my final momentum minus my initial. And that's going to give me a change in momentum, an impulse, of 9 kilogram meters per second. All right. And so you'll notice something here is that the impulses of these objects colliding are the same, they're just opposite in direction. So this is going to be consistent for all scenarios, and you guys should have seen this in the activity today as well, where when objects collide, they experience impulses that are equal and opposite. So very similar, or basically the same as how two forces will interact when with our action and reaction pairs from target 2. Okay, so what we could say is that objects within system can change momentum. And I'm going to draw an arrow basically going right here, showing that. All right, so objects within a system can change momentum. All right, but now let's look at the total momentum of our system. And remember, that's really what the conservation of momentum law is going to be looking at. So if I just look at my whole system right here before, I'm going to add up my momentums, 5 plus -3. That'll give me a total momentum of my system at 2 kilogram meters per second. All right, now let's add up afterwards. Again, I'm going to be looking at my whole system of both the blue and the white object. -4 plus 6 is going to equal 2 kilogram meters per second. And so my total momentum before is equal to the total momentum after. Momentum is conserved, it doesn't change. And that makes sense because even though objects are changing momentum, their impulses basically cancel each other out since they're equal and opposite, right? We have a negative and a positive 9 here. They basically cancel each other out. So there's really going to be no change from before and after. So even though objects within a system change momentum, the total momentum of a system remains constant. I'm going to draw an arrow showing this right here, right? So when we went from our system before and after, no change in momentum. Right? So that's basically the law of conservation of momentum, and we're going to be looking at that law through multiple scenarios. So I'm going to draw scenarios right here, right? And we're going to have elastic collisions. We're going to have inelastic collisions. And we're going to have recoil. Right? And elastic collision is basically when objects are going to be bouncing off one another. And that's an example of basically right here is what we saw, right? The objects collided, they bounced off each other. So I'll draw a quick picture of it. Object is going at each other. They collide. And they go off in different directions. Right. We're going to have an equation for this, and really the equation is the top one right here. The momentum before is going to be the same after. But we could also write momentum as P equals mv. And so instead of writing P, we're just going to put mv in. And we're going to need to do it for both objects. So we're going to have before and after. Even though it looks like a long and complicated equation, it's really not that bad. All right, so I'm going to look at my momentum of my first object, m1 v1, plus the momentum of my second object, m2 v2, and that's going to equal the momentum afterwards. So still m1 v1 plus m2 v2. All right, and that's for an elastic collision. So let's now look at an inelastic collision. Right? So maybe when objects stick. So what do I mean by that? Basically, we have two objects. Let's say this one's still, this one's going at it. Afterwards, what we're going to see is these objects are going to stick together. You know what? We could even have this object moving this way. It could be like two linemen going at each other. They'll stick together and move. All right? And so we're going to have a similar equation here, right? We have object 1 and 2. And so it's going to be the same in the beginning as our elastic equation. So m1 v1 plus m2 v2. So object 1, object 2 is going to equal m1 plus m2. So since they're sticking together, we could treat these two masses as one object and worry about just one velocity here. All right, so that's the only difference. It's just the fact that we're going to treat now this object as as these two masses as one object right here. All right, so let's look at recoil. Recoil are basically going to be objects moving away from each other, but I guess the best example would be maybe a cannon example, where we have a cannon beforehand with a ball in it. And then when that cannon fires, when that gunpowder explodes, that cannon's actually going to, the ball, of course, the cannonball is going to move forward. But that cannonball, or the cannon itself, is also going to move backwards. Okay? And so how we're going to write this one is, at first, these two masses together, they're basically together. We could treat them as one object. So we're going to say m1 plus m2 beforehand. We're going to have the same velocity. In this case, it's just going to be 0. It's going to be equal to our momentum afterwards. And in this case, our objects separate. So we have an object here, an object here. We can no longer treat them as one object because they're going to have different velocities. So it's going to be m1 v1 plus m2 v2. Right. And so here are situations of collisions where our momentum could be changing, but our total momentum of the system is going to stay the same. And this is really what these equations, even though they look complicated, are really getting at. And so we're going to explore in the next video or next class is how to go about solving problems using the ideas learned here, the principles here, and the equations in these situations here.